again. We were covering pass transistor logic. Last time, just to remember, we covered all these subjects: diode logic, resistor transistor, diode transistor, transistor, NMOS, CMOS, dynamic logic, domino logic. There's one more logic maybe we should talk about. That is the pass transistor logic. We can consider this transistor as a switch. We discussed that, and then we found out that NMOS is good in transmitting low. So this was good. If the input is 0, output is 0. But we noticed that if we use NMOS as a switch for the VDD, transmission of high voltage, it's not so good. So if the input is VDD, output becomes like this. Okay, so it's not so good. VDD minus threshold of N. And the threshold of N is this transistor's threshold. Switching transistors threshold, of course. So similarly, we look at the PMOS transistor, and we notice that PMOS transistor is good in transmitting high voltages. If the input is 5 volt, output is 5 volt. So that's good. That's good. So we say that if the input is 5, output is 5. But in the PMOS, if the input is unfortunately, if the input is 0, output is not so good, VTP. I mean, this doesn't mean that we give the input and then output is pulled up to VTP. We should look at from the other concept and then say that when there's a CL charged up to 5 volt, we can discharge it down to VTP, absolute value of it. Okay, so 0 doesn't become 1 volt. Already the 5 volt at the VCL can be dropped down to 1 volt only. So therefore, when we think about both of these, we can come to transmission gate. So the best thing, if you want to use this transistor as a switch, is to use both NMOS and PMOS at the same time, and then 0 volt will be transmitted as 0 volt, and 5 volt will be transmitted at 5 volt. But in any case, when the NMOS is used and 5 volt is transmitted as 4 volt, that's not a big deal, maybe. But in typical thing, that's what we use as a CMOS. So now, if we want to make a logic out of this transistors, pass transistors, we have to think carefully here, and then look at this as maybe you can just erase this and then say that, okay, this looks like A and B, but really it is not. So this is not a good way of representing. Okay, so the point here is that let me start from the beginning. Maybe I should just erase this and then start from the beginning. Might be better and easier instead of trying to do this. So here, the concept is going to be like this. You know, here, when B is equal to 1 in this logic. So B is 1 means, you know, logic-wise, that means 5-fold, of course. So if we apply here 1 and then if we apply here 0, output Z is going to be equal to A. Okay, but this doesn't mean that Z is equal to A dot B, although it looks like it, because when B is equal to 0, okay, Z is floating. Okay, so therefore logic is halfway correct, but you know, this is not really you know, resulting in this. Okay, so therefore you know, there is a motto here: we should be careful, never leave the output port floating. Okay, so when we use this logic, we should just be careful and try not to leave the output floating. So how can we achieve that? I mean, there are ways to achieve this. One way is maybe just to do this. I mean, we can use the other transistor as like this, if it's okay for us to not to use the CMOS. But if we do this, like this is B bar, this is B, and then this is A, and this is out, then we really have the correct logic, because this is going to be A and switch B, and then this one, when you know B is on, B bar is going to be switched like this, B bar. So therefore output is going to be, Z is going to be equal to really A dot B. Okay, so why is this the case? Because if in this case B is 1, B is 1, then Z is equal to A. But when B is equal to 0, Z is equal to what? 0. Okay, so it's not floating anymore. So logic-wise, if you look at this logic, this is equal to A dot B. B is equal to 1, the result is A. B is equal to 0, the result is 0. So we need to make sure that you know, there is no floating case. And if you want to make this thing out of maybe CMOS, you know, then you will be consuming a lot of transistors, but it is possible to make this. Maybe you will be putting A here. I mean, instead of one transistor, you can put a switch here. This is B, and then another switch here, which is B bar. Okay, so that's going to be the CMOS switch. And you can also put here a CMOS switch. By putting a CMOS switch here. This one goes to, this one goes to B bar. This one goes to B. So I can therefore draw this as a switch and then do this like this one. Here, this switch is connected to B bar and this switch is connected to B. Okay, and this is going to be output Z. So this is a full CMOS representation. Just maybe CMOS switches. Whereas here we obtain the same thing with only simple, NMOS switches. Or NMOS transistors as switch. The voltage drop, if it is not that critical, we can also use this version. I mean, this version, voltage drops will occur. When A is high. Okay, so output will be, note that output is going to be VDD minus VTN, for that case. So, you can notice and then, do this one. So there are different implementations of this case. And notice that again, when you want to do this A.B circuit, you need to do maybe A here and then B as a switch control signal. And this is Z. And this one is going to be again an NMOS. And then here, B bar. Okay, but instead of connecting this here to ground, because you don't want to maybe consume your signal with ground signal, then you can connect this. Remember, when does this happen? B is low, then output needs to be 0. So you can connect also this one to B. Okay, so instead of ground, you can connect this to B, because you need that when B is equal to low. So this is the way, and then that means we can consider, and then do this. Z is equal to AB. And the first thing, which is very important, is never leave the output port floating. Output port floating. Okay, so for all cases, you have to make sure this. Okay, so here you do not need to use VDD or ground here. Instead, you can use the input ports to achieve this. Okay, so you have to be, looking at the circuit accordingly. So this is maybe another way of doing it. Okay, instead of just using A here, so instead of just using A here, like that was the case here, right? Why we were just using A. So you can use A bar. So this is probably better way of implementing this logic now. And how can we do this? When B is high, okay, or logic 1, what happens? Z is going to be what? This will be on. This will be both off. So therefore, Z is going to be equal to A. So if A is low, it's going to be low. A is high, it's going to be high. So the signal is coming from the A input. So when B is equal to low, okay, maybe I should use a different color here. Okay, just to get a better. When B is low, then this will be off. I mean, this will be off, both of them, and this will be on. Therefore, Z is going to be equal to A bar. Okay. So why or what happens now? So we have what is the logic here? Okay, so we can look at the concept here. What is happening here? The concept here is actually a multiplexer. So input 1, let's say this is input 2. So for this case, I mean, we can just look at and then draw the circuit like this. I mean, instead of putting the full switch here, just to show you the concept, if this is switch, this is B bar, then Z, and the Z is going to be okay, output. Z is going to be input 1 when B is equal to high, and then it's going to be equal to input 2 when B is equal to low. So we have achieved a multiplexer here. So this multiplexer idea can be used to make a logic circuit now. And we can, I guess there's a mistake here. So I should be correcting this. This is just an NMOS also. And this is NMOS transistor. So if the A and B and then all these are placed like this, this is going to be also a logic, like when B is equal to 1, Y is going to be equal to A, and when B is equal to 0, Y is going to be equal to B, and since B is equal to 0, output is going to be 0. So this gives us the logic, Y is equal to A dot B. Okay, so it's correct. For this other case, the bottom case, what is Z? So how can we find out about Z? You know, when B is equal to 1, Y is equal to A bar, and when B is equal to 0, Y is equal to B. So what is this logic? Why we call it Y? It should be Z, right? I mean, this should be Z. So the logic is that Z is equal to A bar dot B. So for all cases, is this verified? Yes. So the switch, this is also a possibility of making this logic or different type of logics. So when we look at this, let's say this is again NMOS. Here, Z, when B is equal to 1, then NMOS, or this one is going to be on. Okay, this one is going to be on, but this one is going to be off. So Z is going to be equal to A bar. Let's use a different color here. So when B is equal to 0, Z will be equal to B bar for this case, and then B bar is going to be 1. Therefore, you know, with this circuit, what do? What is that? A bar or B bar. Why? Is this correct? When B is 1, this becomes 0. Therefore, output is A bar. When B is 0, then this value is going to be 1, and it doesn't matter what is A or A bar, so it's going to be 1. So correct. So this is, you can implement OR circuit here, pass transistor logic. You know, this is the way that you implement OR. I mean, if you replace this like with A bar, B bar, actually that's what you're getting, you know, A bar or B bar. Those were the inputs, right? So instead of A bar, I mean, you can use the inverse of these things, but you know, this is OR implementation. So I mean, if you look from the other perspective, of course, you can say that this thing is A dot B. You know, but you know, if you think that this is the input A, this is the input B, then it's going to be, you know, OR implementation. You can just play with the, you know, inverses and other things, and then you can get AND, OR, NAND, NOR, you know, those kind of different inputs here in different cases. So other than the voltage drops, only, you know, these two transistors, you know, if we ignore the voltage drop cases, then we can, you know, implement these again with only two transistors. So this is kind of covers up the different type of logics. I mean, this pass transistor logic, I mean, it's good to know. It's not used widely, but it's good to know about this. So any questions? The most important note here is that, you know, when you do that, never leave the output port floating for any of the cases. Okay, and then this is an important case. Maybe I can put here an option. This one here could be B. It also works like that. Okay, so if you don't have questions, I'm going to go to the next subject. Next subject is this one. I uploaded the slides also. You know, we finished logic types, TTL kind of logic, or NMOS logic, CMOS logic, but there are other type of circuit elements that are used in logic design. And, you know, these are the things that we will be covering: regenerative circuits, and these include bistable, monostable, or astable circuits. We'll see what it means and how can we implement them in some, you know, transistors, or sometimes we'll be using some elements that are available in the market, including the timer circuit that is available in the market. How can we generate clock signal, for example? That's what we will be learning. Or how can we make some other interesting circuits and memory, whatever. After these, we'll see memory structures. Also, it's a part of the digital world. You know, you want to store ones and zeros. You don't want to just do actions here. So when we talk about regenerative circuits, there are maybe we'll be considering three cases here. And One of them is going to be bistable multivibrator. And in this case, we have a bistable situation, okay? So bistable means there are two stable states, okay? And then one unstable state. Okay, so I think, you know, you need to see the whole maybe forest to understand the concept, but I will be, of course, talking about each individual, maybe three. And until you see the full forests, it's going to take a little bit time for you to understand the subject. And now we want to explain these subjects maybe conceptually. You know, the stable states are going to be, you know, maybe an output is going to be at 0 or 1, okay? So output can be 0, logic 0 or logic 1, okay? But in the circuit, there's going to be a case, and you know, we can think about this as a ball. So this is maybe a simple way of explaining here. So this ball that we are thinking, like, is it going to be here, logic maybe 1, you know, we don't know the state. I mean, we can define this as state 1, stable state. Okay, the ball, if you put a ball here, this is going to be an unstable state, state 3, let's say. Okay, but if the ball is here, this is going to be stable state. Okay, so I mean, of course, for us, the stable and unstable states are going to be not unstable, but there are two states here. You know, states are for us is either logic 1 or logic 0. Okay, but conceptually, the output of a circuit can be either 0 or 1, but we can change maybe with some kind of action. You know, from 1 to 0, we can switch the output. So this could be a memory case, for example, and then we switch from 0 to 1. But how can we do this? We will be learning how we can do this, you know, with the circuits that we will be analyzing. So monostable multivibrator means there's only one, let's say, one stable state. Okay, and there are some real life, you know, applications of these things. So let's say the state is staying at 0. There is no alarm, no nothing, but there's a disturbance. Disturbance in the system. Let's say a burglar is coming and trying to open the door and opens or breaks the window, okay? So it creates an unstable state. And then alarm will go on or alarm will go off, and then, you know, make a noise, whatever. And then after a certain time, we can say that you know, go back to stable state. So, you know, for a car, let's say you make a system and normally there is no sound, but somebody is trying to open the door and then alarm goes off, and then starts, you know, making a big noise. But after 1 minute, if we set it that time to be 1 minute, then it turns off. Okay, so therefore here for such circuits we have unstable and one stable state. But sometimes we want the circuit to go switch between 1 and 0. Okay, so maybe the state 1 here, okay, is state 1, and then this goes to state 2. Okay, so for this circuit there are 2 unstable states. Okay, so the system goes back and forth between these states forever. Okay, so this is what we need, for example, if you want to create a clock. Okay, so good for clock signal generation. Okay, so these are the conceptual explanation of different regenerative circuits, and then how we can obtain them is going to be another issue circuit wise. But as we discussed, for example, for logic, what is AND operation, what is OR operation, these are the conceptual explanation of these circuits. So what we use to create these kind of circuits, I mean, this will have its own advantage and usage. This will have its own advantages and usage, and this will be another one. Okay, so like this is maybe for alarm circuits. These are for clock circuits generation. And this also has maybe other usages, but it's maybe for memory, memory. So we can store the signal as 1 or 0 because it will be staying at 1 or 0 until we want to change it somehow. So now the circuits that the basic block of the circuit that we will be using to generate all these 3 multivibrators is this comparator. Okay, so the comparator is typically an op-amp. So okay, so this is an op-amp. I guess you learned about op-amps in the past. So if you have an op-amp, ideally the gain, the response of the op-amp is going to be like this. Here we call the A input and B input. So this is a negative input and positive input. So ideally we have currents as 0. It's an ideal op-amp. Okay, and then ideally ideally A, the gain is here. The gain is infinity. So ideally, A is infinity. Therefore, if we call this thing as E signal, E is equal to VA minus VB, then output VY is going to be, if signal is a little bit plus sign, amplifier gain is high, and then it goes and saturates at Y1 or V1, okay, because the highest supply voltage is plus V1. If the signal is a little bit negative, then it goes and then to the other extreme, minus V1. So this is the ideal response of an op-amp, but we will call this thing not as an op-amp, but it's going to be called as comparator, because we are comparing A and B. If one of them is larger, it goes to output goes to V1. If B is slightly larger, then output goes to minus V1. Okay, so this is the ideal case, but actually, the gain is never going to be infinity, and then the signal is going to be like this. Okay, so this is practical case. IA is finite. You know that maybe it's 10 to the power 3, like the gain maybe 1000. So it's very large, but it is not going to be infinity. That's more realistic. So, without knowing the value of A, thinking that A is not infinity, then we can look at the output and then write the output signal for all these 3 cases. So like this is the case 1, 1, and this one, okay? So for the signal, when error signal, input E, which is VA minus VB, is larger than V1 divided by A, then output is going to be like this is the case, okay? So, and then maybe we can call this thing as case 2, and then this one as case 3. Okay, so, okay, now we can say, why are we doing all these? We will just use this element, this comparator. It's very useful. We can make bistable multivibrator with this element. I mean, soon it's going to be maybe more clear. So, if that element is connected like this, this will be very interesting circuit connection. And with this circuit connection, we can make either bistable multivibrator or monostable, or even maybe astable circuits. I mean, we'll be maybe seeing this soon, okay? So if you, typically for an op-amp, remember, if you want to make an op-amp as the amplifier, we connect this side as the ground, maybe this side, like this is how we connect the feedback circuit, okay? So this is R1 and R2. and therefore, we create a gain circuit. Okay, typically the feedback is connected to the negative port. Okay, however, in this circuit, typical amplifier, okay, amplifier, but we don't want to make an amplifier. So therefore, this side is connected to plus side as the feedback. R2 is connected to here. And, or maybe, this is just one type of signal that we have. So what happens here? I mean, let's look at it. And what happens here? So, I mean, typical equations are this. E is, again, equal to A VA minus VB. So VA and VB. Here VB is connected to V in, but VA is generated out of VY. The feedback signal is taken from VY, and then VA is generated, okay? From VY. This is as connected to VN. Okay, so therefore, if we look at the circuit and say that E, since VA is generated from VY, how is it generated? Because here the current is, going current is equal to 0. So there is no voltage drop due to the input impedance here. Therefore, VY or VA is equal to R1 divided by R1 plus R2 times whatever the VY value is. Okay, so this value, we can call it as K, or we can call it as beta, or we can call it as feedback gain. Of course, this gain is going to be less than 1. So, I mean, now you can be curious, why are we talking all these? It will be clear soon. But if this K is replaced by this with K, then the E value is going to be K minus, or K times VY minus Vn. Okay, so this is also fine, let's say. Okay. So why do we care about this? It will be soon, clear. So that A times K value, what is A times K? What is A? A is this gain, okay? Gain of this circuit. We know that VY is also equal to, for different cases, VY depends on E, but it is depending on 3 cases here. So that will be different for each cases. Okay, but the gain is going to be A. So if the gain of A times this K is less than 1, typically this is not going to be the case. Why? Because A is 1000 and K is maybe 0.5. Okay, maybe it's going to be 0.1. Okay, so this is rare. but possible. Okay, so that means the feedback times your gain is less than 1. Okay, so if okay, this is assumption. So if this is the case, we can look at for this circuit connection. Now this is V in. Okay, now this is V in. And then our circuit is connected like that. Now we want to obtain Vy versus Vn. Vy versus Vn. Vy versus Vn. Okay. So we can look at this for different extreme cases. And let's say when Vn is equal to goes to minus infinity. Okay. So what happens? If Vn is minus infinity, it doesn't matter what the value of Va. You know, here is minus infinity. So the E will be positive. E is going to be positive. If E is positive, the output signal is going to be V1. So for this extreme cases, it will be V1. Okay. So this will continue because V1 is the output, then VA can be calculated. And the output, remember this equation here, as long as E is larger than V1 divided by A, output is going to be remaining in here. Okay. But when E becomes, remember this is the boundary, okay, boundary 1 is the point where E becomes V1 divided by A, then things will start changing. So what is VA or E? What is E? Remember from the equation, E was this value, and this we said this is K, right? And so therefore, when this is the case, K times V1 minus V in. And here we can find for which value of V in, things will start changing. Okay, when V in starts increasing, the signal will reach to this value, and therefore E becomes maybe changes its value. Okay, so which value of V in, we can find this and by leaving V in alone. So the point where V in becomes A times K minus 1 divided by A times V1, that's the point where the output will start going into this stage. Okay, so this was 1, remember? So this is the case where the signal is 1. And for this value of Vn, which is A times K minus 1 divided by A times V1. V1 was this voltage, of course. Things will start changing. Okay. So we can look at the other case. This is the number 3. What happens number 3? So region, maybe I shouldn't say boundary, but region 1 boundary. Okay, so that's how we can find the boundary of region 1. Okay, so this is the boundary. We can do the same thing for region 3. So for region 3, the output is when Vn goes to plus infinity. So if Vn is plus infinity, then this signal is going to be negative, because the negative side is plus infinity. So E becomes minus infinity. Okay, E goes to minus infinity. Here, when this is the case, E goes to plus infinity. So if E goes to minus infinity, we know that this is the extreme case, and then output becomes minus V1. So the signal is like this. Now we come from here until the signal starts changing. Okay, so this is the boundary, the under one, and then this is boundary 2. How do you find boundary 2? So one side was this one, V1 divided by A. The other boundary is this case. Okay, so the other boundary, let me do it maybe different color. This one, okay? So this is the other boundary. And so how can we calculate that? Boundary 2, region, region 3, boundary. Okay. It is the point where E is equal to minus V1 divided by A. So again, if we do that, this is the K times, this time minus V1, because that's the value of Vy, and minus Vn. We can find that value, and the value of that Vn is equal to minus, this time, A K minus 1 divided by A times V1. So this value here is therefore equal to 1 minus AK divided by A times V1. Okay. And that makes sense because we said that what did we say? We say AK is less than 1. Okay. AK is less than 1. Maybe I should select a different color. Okay. So if AK is less than 1, then this is positive. AK is less than 1. So, okay, that's the other boundary. What happens in between? The between is actually the signal is linear. The signal is this much, A times E. Therefore, the signal is going to be like this. So there's a linear relationship. I mean, this is just maybe a tedious thing, and then not maybe very, interesting right now for this case. Yes, in between Vy is equal to A times E, and then E is equal to Vy divided by A. Therefore, you can say that Vy, I mean, if you do the math here, is going to be equal to just the slope minus A divided by 1 minus A times K times Vn. Okay, linear relation. But this is not interesting. I mean, so what? If the input is one value, Vy is going to be another value. Okay. So depending on Vn, for each Vn, we have one V out. For each Vn value, we have one stable Vy value. Okay. Not very interesting. Okay. The very interesting case is going to be here. If which is the case anyway, A times K is larger than 1. Okay. Which is usually the case. Okay. So let's obtain this graphic again for this case. And then we will go to Vn goes to minus infinity. Here, I mean, I'll do this now a little bit quicker. Why? Because we did it here already. So the same circuit, Vn goes to minus infinity. Okay. When Vn goes to minus infinity, that means E goes to plus infinity. Okay, so if E is plus infinity, the output value again is going to be V1. So the signal will be coming from here. Oops. V1 value here. Okay, so the signal is coming from here, V1. And then we already solved the value. And then the boundary, remember the boundary is same. If you just make calculation, you know, this is the boundary value. But this time, since AK is larger than 1, the value that we found here, boundary 1 is same. Okay, which is V in equal to AK minus 1 divided by A times V1. But that value is going to be positive now. So that value is going to be here. So this is going to be AK. Maybe I should write it like this. This value is going to be AK minus 1 divided by A times V1. That means, you know, when you keep increasing this, increasing it here, up to here, nothing will change. But this V in is positive now. Okay. What happens if V in goes to plus infinity? Then E goes to minus infinity. Oops, we didn't give a break, huh? I forgot. I keep explaining, but I should explain this, sorry. So this time, the signal is going to be minus V1 coming from positive here. And the boundary 2 is going to be negative this time. So this value is going to be minus AK minus 1 divided by A times V1. So this is very interesting. And, you know, for input 0, what is going to happen? What is the output for input is equal to 0? I don't know. So if you calculate for this state, now this is case 1, this is case 3. Where's case 2? Okay, this was 1, this was 3, this was 2, right? So this one, where is number 2? That's interesting. So this will be for number 2. Okay. So output, this is the critical point then. When the output is minus V1, we can call this thing, let's say, state 3. Okay, stable state 3. This is a stable state. 1. Or I don't know how to call this thing. But there's another state here. let's say state 2. So for input, V in is equal to 0. Okay. Vy can be either V1 or 0 or minus V1. Okay. And the way that it switches between the states, let's say it comes like this and let's come like this, like it stays like that. And then when it comes here, it switches to here. And then you keep increasing this way. The other way around, if we decide to change the signal, let's say like this, you come from here and here and here, it stays stable, stays stable, stays stable, and then, boom, it switches. Okay, so if the signal input is 0, it's really important where you come to that point. So this is not stable state, not stable. Okay, so this is the case then. Now I was explaining this, maybe I changed the numbers and names, but let's say this is S1, this is S3, and this one is S2 case, okay, not stable case. So we can obtain such a value. For input 0, output can be either 0 or output can be V1 or V2. So it depends on the history and the past signal, you know, what was happening, if the signal is coming from this side or from the other side, okay? So this is now going to be you know, useful for us for maybe, I mean, it's going to be clear and useful for us soon. So let me call this thing as M just for simplicity. And then we will be seeing the application and use of this maybe after giving a break. Okay, so I'm giving a break. Do you have a question right now, or after the break you can ask the question? Evet. Okay, so let's go back. Okay, I hope that things will be clear soon. I know it was a little bit confusing here. You know, just to summarize, what we did was an interesting connection of this circuit. This circuit, you know, we connected the output to the plus port, and that was actually a positive feedback. And typically we like to make negative feedback, but we utilize the advantage of this circuit, and the circuit is functioning interestingly with this case. And if the signal is coming from here, let me draw this here, and then it will be switching to here and then like that, okay? So on the way back, however, if the signal is coming from here, it will be going and then switching and going like this, okay? So we will be using this to our advantage to make bistable circuits. Okay, so that's the bottom line here. Bistable circuits, how we can obtain it and then use it to our advantage. So let's go to this example again. Here is the summary. So I call this one as M for simplicity. Okay, this is M right now. So okay, hold on a second. Alo. Onaylıyorum. Dersteyim. Görüşmek üzere. Sağ ol. So this is the same thing, just to repeat things. If the signal is coming from here, it will be switching down like that. But if the signal is coming from this other extreme, it will be going and switching like this. Okay, so and we won't be able to observe this one. So this case will not be observed, okay, for our case. So so we can say that the circuit we can say that the circuit has memory. Okay. The output depends on the previous path of the input. Okay, so what can we do with this? I mean, a typical example is this one. You know, if the input, let's say this is Vn, this is the time scale. Okay, time. time. Okay. And then this is your input signal. Okay. So if we have a response like this, we can draw the output. So the signal is coming from minus. So that means it's coming from here. So the output is going to be, let's say this is t is equal to 0, t, and this is Vy. Vy is this one. So if the signal is coming from minus, then output will be equal to like this. Okay, until when? Until this point. So assuming that this is correct, whatever. Slightly shifted, but maybe this point, okay? So until that point, which is T1. Until T1. And then with T1, the output switches to, oops. Why is it doing that? Interesting. It goes to here, minus V1. This is V1. Okay. And then that's T1. For T2, it will not be switching at all. So let's say this is T2. Nothing happens until it reaches to this point, T3. So when it comes to T3, it goes back up here. So what? So this looks stupid, but it's okay, you know. T4, somewhere around here, nothing happens until it comes to T5. This is T5. Okay. So that's how it goes. This is normally, I mean, not very interesting, but we can obtain a square wave signal. Okay. So this is square wave. Signal. Okay, so generated. So what you know, what is the point here? I mean, we could just make an you know, you could just do this, right? I mean, you could just put here the sine wave, and then, you know, high, low, high, low, high, low. You could obtain that. But the thing is, if your signal, the sine wave, had maybe some jitter on it. Let's say the sine wave has some maybe, let me do it like this maybe. If the sine wave had some jitters in here, okay, some noise, then each time that this was crossing up and down, you would be having a noise. So, you know, if the signal that you have here was a simple op-amp, and was a simple op-amp that you have here. Each time the signal was coming and then going down, let's say, while it's going up, going down. So the output would be maybe just, coming in here, going up, and then for a short while, and it comes down, and then goes up again, right? I mean, this would be causing, okay, maybe a jitter, glitches, could be caused. However, here, that feedback mechanism or bistable connection prevents this, okay? This is for simple op-amp case comparative. So, in our circuit, however, this is going to be, again, will be happening. Okay, not a very good drawing, but okay, without any glitches. Okay, so that's one maybe application, and we can obtain a nice clock signal without any glitches. Okay. Why? Because, like, this doesn't change until here, and then once it's in there, it doesn't change until here. So the signal switchings occur here and here, and then again here. Okay, so therefore the clock is nicely, made immune with any glitches here. Okay, so T5, T3, and T1. So that's just, one application, and there are other applications of this circuit. So we can obtain maybe another bistable circuit using CMOS circuits. If you put these two inverters back to back, and then let's say you have again, this is the response of the inverter. So let's say it's not a ideal one. So this is the slope. The slope here is A, okay, or minus A, whatever. So A is minus, or rather, okay. So what happens here? Do we still have the same concept? One stable or two stable, one unstable state. Yes, that's what you obtain also here. So if the input is V in V out graph is formed, let's draw this. This is, let's say, output is VDD. So the output is changing between VDD and ground. So here, let's say this is going to be your response, V in, V out 1, because it's just an inverter. So this will be same as this one. So I'm just drawing this a little bit extreme case. Okay. So this is the point VDD divided by 2 point. And this is VDD divided by 2. Okay, so this is input versus output case for the first one, and exactly similarly V in 2 and V in 1 is going to be the same thing. And then this is how it's going to be giving the response. So this is VDD divided by 2, and this is VDD. So V out 1, V out 1, V out 2 graph is going to be similar. But the circuit is connected, so V out 2 is equal to input. V in, V output 2 graph. How can we draw the V in, V output 2 graph? Now, you know, the signal change, this is going to be slope of A, and this will be also slope of A, okay? So the response, if you do this properly, the response is going to be like this. So output is going to be input 0, output is going to be 0. But this time, the signal output is going to be switching like this. And this is going to be VDD. So this point is again VDD divided by 2. So if they are not connected, this would be our response. And this would be VDD divided by 2. And the gain here would be slope would be equal to A square. So, you know, when does this signal change? I mean, you can find it from here, this point, where it's corresponding to here, and that input is going to be switching. So, you know, this point and this point will correspond to here. So, you know, those values are going to be, you know, from the gain values, we can calculate that. So that value of V in is the point where this becomes like this one, and then it becomes like this. So sorry, you know, maybe I'm not in the board, so it's difficult to explain. But we also know that the signal is like this because their circuit is connected to each other. I'm sorry. Okay. So 0 input, output is 0. The circuit is connected. And then this is also output. So that means, I mean, the bottom line is this. In this device, if the input is 0, okay, if the input is 0, this is going to be 5 volts. This is going to be 0 volt again. So output will remain in here. So this will be stable state. One of the stable states is input is 0, output is 0. And the other stable state is, let's say, stable 3 state is this one. When input is VDD, output is going to be VDD. So this is VDD. So if this is state 3, this is VDD, and this is going to be 0 volt. This is going to VDD again. Okay. So if the input is 2.3 volt, so that's the interesting case. So let's say this is 2.5 volt. This will be 2.5 volt. This will be 2.5 volt. And that's this state, okay, S2. So that's going to be also a solution to the circuit, but that solution is going to be not a stable case, because if this becomes 2.51, this becomes 2.48, and then this becomes 2.53, and then, you know, it goes to one of the states, stable states. So we can call this thing also as a bistable multivibrator. Again, we have 2 stable and 1 unstable state. So, I mean, this looks trivial to you, but this is actually a memory element. And then we can, you know, make an SR latch out of this. And then we can make a memory out of this. So I guess I will be talking about this next hour. Just to wrap up what I mean, this could be maybe made with maybe 2 here NOR gates. Okay, 2 NOR gates are going to be making this memory for us. And then the same thing, if we switch the circuit and then use one of the inputs as this case here, this will be look like, you know, we can connect here reset signal, and then this is going to be set signal, and then this will look like, in fact, this circuit. Okay, so this one is going to be reset, this will be set signal, and that's how we can obtain an SR latch. Okay, so that's the basics in this SR latch, and we can make a memory, as I told you, from these 2 stable, 1 unstable state. Okay, so I'm going to stop here because the time is up. And if you have any question, please ask now, or we can stop now. Any questions?